Hello world, it's Siraj, and let's build a game bot that learns how to get from point A to point B using a special type of reinforcement learning called Q-learning. Reinforcement learning means learning by interacting with an environment through positive feedback or reinforcement. It's similar to how you give a dog a treat, but only if it rolls over, and it's evolved over the past few decades. In the late 1950s, an American mathematician named Richard Bellman was trying to solve what he called the optimal control problem. This describes the problem of designing an agent to minimize some behavior of a system over time. Eventually, he and his colleagues finally discovered a possible solution to it, which was later called the Bellman equation. It describes the value of a problem at a certain point in time in terms of the payoff made by previous decisions, and it also describes the value of the remaining decision problems that result from the initial decisions. By involving a system's various states in this way, it broke the problem down into simpler subproblems. The Bellman equation is now used in many fields. It helps with minimizing flight time for airplanes, maximizing profits for hedge funds, minimizing the beef that Soulja Boy seems to have with everyone.
Y'all trying to beef with Soulja?
No.
Siraj, they want some beef with me.
So Bellman's squad was making waves throughout the math community, but meanwhile a psychologist named Edward Thorndike was trying to understand how learning works. By studying the animal kingdom, he came up with what he called the law of effect, which states responses that produce a satisfying effect in a particular situation become more likely to occur again in that situation, and responses that produce a discomforting effect become less likely to occur again in that situation. Thanks, Captain Obvious. No, it was actually a pretty important discovery. One of his experiments was putting a cat in a wooden box and observing it while it tried a bunch of different ways of getting out until it finally hit the lever that opened the box. When he put the cat back in the box, it immediately knew to hit the lever to get out, and it was able to do that because of the process of trial and error, which is what Thorndike was essentially describing in the law of effect. A couple decades later, a British computer scientist named Chris Watkins thought that perhaps these two ideas could be combined to create a new type of learning algorithm. The idea of designing an agent that minimizes some behavior of a system over time, like the Bellman equation, and does so through the process of trial and error, similar to the law of effect. And so he invented a novel reinforcement learning technique he called Q-learning. So what is this? Let's say we had 5 rooms in a building connected by doors, and we'll just think of everything outside of the building as one big room. All of space-time is room 5. We can think of this system as a graph. Each room is a node and each door is a link. Like room 1 has doors to both room 5 and 3, so they're connected. Our goal is to put an agent in any room and for it to learn how to get to room 5 through trial and error. So the goal room is room 5. To set room 5 as a goal, we can associate a reward value with each door, which is the link between nodes. So doors that lead immediately to the goal room get an instant reward of 100. Doors not directly connected to our goal room get 0 reward. In Q-learning, the goal is to reach the state with the highest reward through a set of actions. So if each room is a state, each action is represented by an arrow. And the mapping of state to action is the agent's policy. It uses the reward value as a signal to improve its policy over time. And it stores what it has learned through experience in what's called the Q matrix. The rows represent the possible states, and the columns are possible actions leading to the next state. It updates the Q matrix over time as it learns the best actions to maximize the reward. Seems pretty useful, right? Q-learning's gotta be used everywhere in video games, right? Consumer video game bots need to be good, but not so good that a human couldn't beat them. The bots that used Q-learning to master games like chess and checkers, and most recently Atari games, become insanely good at whatever they play. Academic AI learns, while consumer game AI generally just makes educated guesses. It doesn't really learn, and its actions are all scripted. But as different as they are, the two fields are converging as we discover more about machine learning. For example, in Forza Motorsports, you can create a drive-atar for yourself. It's an AI that learns how you drive by observing you and can then imitate your driving style. Having adaptive behavior like this will make games more interesting, and there's a lot of potential for more of it. So let's write out a 10-line high-level Python script that uses Q-learning to train a bot to get from point A to point B. This game is a 5x5 grid. Our agent is the yellow square, and the goal is to find its way to the green square or the red square to end the game. Each cell represents a state the agent can be in, and there are 4 actions: up, down, left, and right. Moving a step will give us a reward of -0.04. The red cell gives us -1, and the green cell gives us +1. So we ideally want to get to the green cell every time. The game world is already built for us, so we'll just start off by importing that at the top. Then, in our main function, we can go ahead and create a while statement set to true, because we want our agent to run indefinitely. Next, we'll initialize our bot's position from our world class and set it to the agent variable. So now we'll want our bot to pick the right action to take in the game world, and the question is, how do we decide that?
I got a grid of squares measured 5 by 5, and I'ma get to green in one piece alive. I'ma make a Q matrix initialize, keeping every single reward of mine archived. Then I'ma pick an action straight out of Q. Then I'ma do it, yeah, each is fresh and new. Update Q with reward on beat, and once I got that, I'll go ahead and repeat, yeah.
We'll use our bot's position as a parameter for the max Q function, which will choose an action from our Q matrix, as well as the potential reward. Then we can perform that action by inputting the action as a parameter to the doAction method, which will return our bot, the action we took, the reward we received, and the updated bot's position after taking the action. Now we're ready to update our Q matrix, so we'll use the updated bot's position as the parameter. We'll print out both parameters to terminal so we can observe the results. We'll run the script by typing in python learner.py into terminal, and it'll pop up as a GUI. The bot will immediately start trying out possible paths to get to the green one, and we can observe the score in terminal improving over time. This bot in particular gets really good really fast, like in 10 seconds. It's already found the ideal path, and it's just going to keep doing it. So to break it down, reinforcement learning is the process of learning by interacting with an environment through positive feedback. Q learning is a type of reinforcement learning that minimizes the behavior of a system over time through trial and error. And it does this by updating its policy, which is a mapping of state to action based on a reward. The coding challenge for this video is to modify this code so that the game world is bigger and has more obstacles. Let's make it harder for our Q learning bot to find the optimal strategy. Details are in the README. Post your GitHub link in the comments and I'll announce the winner next video. For now, I've got to optimize my life, so thanks for watching.